Hello everybody, I welcomes all of you to this last unit. This is the first lecture of last unit, and in this unit we have to see different types of bridges or bridge circuits. Now if you see the bridge circuits, there are different types of bridge circuits, okay, but mainly they are classified into AC and DC bridges. So in this unit we have to cover this AC and DC bridge circuits. Okay, so before starting AC and DC bridge circuit, let us see some introduction related to bridges. Okay, so if you see a bridge circuit, it is mostly used for measurement of resistance or impedance. Okay, so it is used for measurement of impedance. So it can be measurement of resistance, inductance and capacitance. Okay, so I think you know clearly what is difference in between impedance and resistance. Okay, so at this level these basics are very useful to understand the next bridge circuits. Okay, so that's why you must know the difference between impedance and resistance. Okay, so what is the impedance term is related to which circuit and resistance term is related to which circuit, that you must know. Okay, if you see, it is used for precise and accurate measurement. Okay, and they are classified into AC and DC bridges. So if you see why the bridges are mostly used, there are again reasons, because if you see, as mentioned here, it is used for precise and accurate measurement. Okay, and if you see the accuracy, it is directly proportional to the accuracy of a bridge component. Okay, so that's why it is dependent on the null indicator. Okay, so what do you mean by null indicator? That we will see afterwards, don't worry about that. Okay, so if you see some specialized measurements such as impedance of a high frequency or impedance at high frequency, it can be also measured with the help of different bridges circuits. Okay, and the another important thing is that the balance equation of a bridge is not dependent on the magnitude of the input voltage. So what do you mean by balance equation? That also we will see. Okay, so again this balance equation is not affected even if you connect or replace that source and detector or interchanged. Okay, so the balance equation and we can say the impedance or the different types of, we can say, resistance and the null indicator, these terms we have to see in upcoming slides. Okay, so this was all about the introduction. Okay, so why bridges are used? Because it is used for precise and accurate measurement, and at the same time they only depends upon means the reading only depends upon or mainly depends upon accuracy of bridge component like resistor, capacitor, inductor. Okay, not depends upon the source or detector or we can say null indicator. Null indicator is nothing but detector. Okay, so this is the most important thing why the bridge circuits are used. Okay, now if you see the classification as discussed earlier, they are classified into two types mainly. One is DC bridge, another is AC bridge. So if you see DC bridges, so there are two famous bridges. One is Kelvin's bridge and another is Wheatstone bridge. Okay, so I think you may have used this Wheatstone bridge many times previously, also in sensors and we can say transducers also we have seen that. So if you see the AC bridge, this is capacitance comparison bridge, then inductance comparison bridge, then Hayes bridge, Maxwell's bridge, Schring's bridge and Anderson bridge. Okay, so these are the bridges, AC bridges. Okay, so first of all we will start with basic bridges, that is DC bridges. Let us start with one most important DC bridge, that is a Wheatstone bridge. Okay, now if you see the working principle of this Wheatstone bridge, it operates on a null indicator principle. Okay, so when there is no current flow through the null indicator or null detector or current sensing meter, we can say the bridge is balanced condition. So what do you mean by null detector or galvanometer or current sensitive meter? So this is denoted by this one. So here the null indicator is nothing but your galvanometer. Okay, which can be also called as current sensing meter. Okay, so here again I am repeating, it operates on this null indication principle. Means what? When no current flows through this galvanometer, the bridge is said to be a balanced. Okay, so the bridge is balanced and there is no any resistance change, and when there is a resistance change, then this will be imbalance. That is the simple technique that can be used for measurement of a unknown resistance, that is Rx. Okay, so the balance equation is found for balance condition of the bridge, or balancing equation that we have to see afterwards. The balancing equation is found for the balance condition of the bridge, and this equation gives us the value of the unknown resistance. So there is balancing equation, and that balancing equation is found for balance condition of the bridge only. Okay, and that can be the value of this Rx can be given by that equation, so that we will see afterwards. Okay, so if you see this circuit, this is nothing but your Wheatstone bridge. So there is voltage applied as a E, this is point A, this is point B, this is point C, this is point D. Okay, now if you see the simple construction over here, the galvanometer or current sensing meter is connected in between point C and T. Okay, now if you see the simple construction of this one, this bridge consists of 4 resistance arms. This is 1, 2, 3, 4, with one battery or voltage source and one null indicator, null detector, or in other words, simple words, galvanometer or current sensing meter. Okay, so normally the galvanometer is used as a null detector. Now if you see this R1 and R2, these are called as a ratio arms. Okay, so the arm consisting the resistance R1 and R2 are called as ratio arms. Okay, and if you see the arm consisting of a standard known resistance, that is called as what? R3, and that is nothing but your, this is your R3 and that is nothing but your standard arm, and Rx is the unknown resistance to be measured. So unknown resistance to be measured should be connected here. These are the ratio arms R1, R2, and this is the standard arm, that is R3. Okay, so the value of this R3 is known. Now how it works, that is very important, and if you understand this working of this first bridge, then it will be very easy to understand the working of next upcoming bridges, because the again the procedure to calculate the unknown resistance is same. Okay, now here the current through the galvanometer depends on the potential difference between point C and D. So as discussed earlier, current flowing through this galvanometer is dependent upon potential difference at this point, this C and T. Why? Because you know that when there is any potential difference between 2 points, then only current flows through that wire. If there is no any potential difference, means if C and D are at same potential, then there will not be any potential difference. Okay, so that's why there will not be any flow of current. This is the very basic thing which you have studied in first year electronics. Okay, now the bridge is balanced when there is no current through the galvanometer. So as earlier we have discussed that the bridge is said to be balanced when there is no current flowing through the galvanometer, or when the potential difference across the galvanometer is 0. The meaning of both is same. So we can say that the potential at point C and D should be equipotential, okay, or equal potential. Now if you see at the time of a bridge, balance potential across the arm AC is the same as the potential across arm AD. Okay, again I am repeating, whenever we consider as a C and D at the same potential, the bridge balance potential across arm AC, means this one, is same as the arm AD, means this one. Okay, so here that's why I can say that the potential at VAD is equal to, means VAD will be equal to VAC. Okay, so here as I am considering the potential at this is same, because the C and D at same potential, then I can write one equation for this, and this will be this equation will be guide for us to calculate the further value of Rx. Okay, so it is written over here. Here IR is equal to I1 R1 is equal to I2 R2. So why I1 R1? Because as we are considering this and this potential at point AC and potential at point AD is equal, so I can write the I1 R1 is equal to I2 R2. So it is same is written over here, I1 R1 is equal to I2 R2. Now if the galvanometer current is 0 at balance condition, I can say that I1 is equal to I3. See here, this I1 is equal to I3, because suppose we are considering no current is flowing from this C point, from C point to D point. Okay, So whatever the current flowing through this point towards this C point, that will be equal to the current leaving to the C point. Okay, so that's why I can say that I1 is equal to I3. So that is written over here, I1 is equal to I3. And if you see this I1 is equal to I3, and if you consider this as a loop, this complete loop, then we can say that I1 is equal to I3 is equal to voltage divided by resistance, because we know that I is equal to V upon R. So V is E and R is this resistance R1 and this R3. Okay, so one important thing I want to tell you that there is a printing mistake, so that's why here R3 is not there, not written over here, but this is your R3. Okay, so here I1 is equal to I3 is equal to E divided by R1 plus R3. Okay, so similarly the same rule can be applied over here also, because here I am considering as I2 is flowing like this, and there is no any current flowing through this flowing from this point C to D or D to C. Then whatever the current flowing towards D point will be current leaving from this D point. So I can say that I2 is equal to Ix, okay, or I4 we can say. So here, sorry, I2 is equal to I4, okay, and that is E divided by R2 plus Rx. So E, this, if you consider this as a total loop, then voltage divided by resistance. So resistance are in series, so that's why they are added, R2 plus Rx. So I2 is equal to I4 is equal to E divided by R2 plus Rx. Okay, so these three equations we have got now till now. This is equation number 1, this is equation number 2, and this is equation number 3. Okay, now substituting equation this 2 and 3 in equation 1, here we can say that if you put the equation, this two equation, and do equation number 2 and equation number 3 into equation number 1, okay, so you will get the equation like this: E divided by R1 plus R3 into R1 is equal to E divided by R2 plus Rx into R2. Okay, so here you have to put the values of I1 here and I2 here. Okay, so here if you see, we will get the equation like this: R1 in bracket R2 plus Rx is equal to R2 in bracket R1 plus R3. Okay, so here what we have done, that keep this into your mind, that is E is removed now and cross multiplication is done over here. So we will get the values like this. If you multiply this inside, you will get the values like this: R1 R2 plus R1 Rx is equal to R1 R2 plus R2 R3. Okay, again R1 R2, if you remove this R1 and R2, or this is same part we can say, so we can reduce this part and we will get R1 Rx is equal to R2 R3. So similarly I can get Rx is equal to R2 into R3 divided by R1. Okay, so here we are getting the value of Rx. So Rx is equal to R2 into R3 divided by R1. So now remember one thing, previously in introduction I have told you that this unknown resistance values depend upon only on the bridge components like resistors or different components that we have to see in future. Okay, but it is not dependent upon that galvanometer or that source. If you interchange that, it will not affect the value of Rx. That is the beauty of the bridge. So that's why in most of the circuits, in signal conditioning as well, bridge circuits are used. Okay, so I think you got the meaning of this, why this balance condition or balance equation does not affect by the source or detectors interchanging. Okay, so I think you got this. So this is all about our Wheatstone bridge. Okay, so if you see here 7.2.2, this is equation number 2, 7.2.3 is equation number 3, 7.2.1 is equation number 1. So this is from book, so that's why it remains as it is. Okay, so I think that you understood this. Now if you see the next bridge, that is Kelvin's double bridge. Okay, so before studying this, you may study Kelvin's normal bridge also, because that is again very simple to understand. So that's why I have directly moved towards the Kelvin's double bridge, because in this bridge Kelvin's basic bridge will be completed or covered. So you can study by your own what is Kelvin bridge, but I think that is not necessary to understand Kelvin's double bridge, because that is covered in this. So let us see the Kelvin's double bridge. Okay. Now, whatever the Wheatstone's bridge that we have seen, that can be used for number of applications, but we must understand what are the limitation of this Wheatstone's bridge. Okay. So it can only be used to measure resistance in the range of few ohms to several mega ohms only. Okay. So if you want to measure the resistance, that is Rx, in the range of Rx in the range of few ohms to several mega ohms, then only it can be used. So it cannot be used for high resistance measurement. That is the disadvantage of this Wheatstone's bridge. Okay. Why? Because in case of high resistance measurement, the bridge resistance becomes so large, so that galvanometer becomes insensitive to show any imbalance, because current will be less in that case. Okay. So it cannot be used for measurement of resistance below 1 ohm. So for that we have to move towards the different types of we can say bridges that we will see in we will see afterwards. Okay. Another thing is that when a large amount of current is allowed to pass through the bridge arms, okay, if you allow the large current to flow through this bridge arms, then you know that whenever the large current is there, heating effect will be there, and that may affect our whole system. So that's why again this is one limitation. Okay, so these are the limitations that we are facing while using Wheatstone's bridge. So although it is having some limitation, it can be used for measurement of resistance in laboratories, resistance measurement of motor windings, relay coils. Suppose if you want to locate some cable faults, then also it can be used. Okay. So it is used to measure resistance of various types of wires for quality control of the wire. That also possible with the help of Wheatstone's bridge. Okay. So these are the some advantages of Wheatstone's bridge. Okay. Now I think you got this equation, and if you understand this equation, then it will be very easy to understand the next bridges. Okay. Let us cover the second DC bridge, that is Kelvin's bridge. Okay. Now if you see this bridge, this bridge is called as double bridge because it contains second set of ratio arms. So these are the second set of ratio arms, whatever the shown over here, A and B. Okay. Now this is the diagram of a Kelvin's double bridge. The second set of ratio arms is formed by resistors A and B, and they connect to the galvanometer here over here at a point O. So this is point O. This is the secondary, we can say, arms. These are connected to point O. Okay, and this point O is connected to the galvanometer. Okay. Now if you see here, as discussed earlier, the second set of ratio arms is formed by the resistance A and B, and they connect to the galvanometer to point O at appropriate potential between M and N. So at appropriate potential in between M and N. Okay. So this resistance, so that's why the effect of the resistance added by the connecting lead Ry from this N to M, that is eliminated. Okay. So now let us see how it works. So here the galvanometer will give the null indication when the potential at point P equals to the potential at point O. So as discussed earlier, there is a balance condition, okay, or null indication only when the galvanometer current is 0. Means what? The potential at point P must be equal to potential at point O. Okay, so this is something different circuitry, but it is very easy to understand. Let us see that. Okay. Now as we can say that galvanometer current should be 0 for balance condition, and means null condition, and potential at P must be equal to potential at O. So if you see this potential at P, that can be called as EPQ. Okay, EPQ. The potential at point P can be called as a EPQ. And similarly, we can say that if it is null condition, and if the potential at P is equal to potential at O, the potential EPQ is equal to potential EQMO, means this Q, M and O. So this potential must be equal to this potential. Okay, I think you got this. This is following some previous state that we have seen. in Wheatstone's bridge like this. So by this definition, this must be EPQ must be equal to EQMO, means this Q, M and O. Now what is EPQ? If you see this EPQ, it is given by E into R2 divided by R1 plus R2. Okay, I think you have seen the lecture that we have covered in transducers and sensors. In that case, I have told you one basic thing, how to calculate the how to calculate the voltage across any resistor. So this EPQ is nothing but voltage across any resistor, and using potential divider concept, this can be given by this formula, that is EPQ is equal to E into R2 divided by R1 plus R2. Okay. Now here E is nothing but, now let us calculate E. E is nothing but voltage. So V is equal to I into R. So I is given here, and how to calculate the R? So I can calculate the R like this. So consider this is R. Okay. So by looking into this matter from this side, I will get the resistance as R3 plus first R3, then it will be series with Rx. But if you see this seems to be a parallel. Okay. So here it can be calculated as AB into Ry divided by A plus B plus Ry. Okay, so this Ry will be having some resistance that you have to keep in mind. Okay, it is not directly shorted, so that thing you have to mind, keep in your mind. Okay, so why this equation is written? Because these resistance are in parallel, A plus B. So if you see, this branch is parallel with this Ry. Okay, so this A plus B is parallel with Ry, so that's why we are getting we can say equation like this. So okay, so this is I think you know how to calculate the resistance when the two resistance are in parallel. That is, suppose R1 and R2 in parallel, then it will be R1 into R2 divided by R1 plus R2. So same formula is used over here. So I into whole R that we have got, that is R3 plus Rx plus A plus B into Ry divided by A plus B plus Ry. So here if you substitute the values of we can say E in this equation, I will get equation something like this. Okay, so what we have done, just we have taken this whole equation and we have put over here at the place of E, and we are getting equation like this. Okay, now consider the path Q to N. Q to N, please consider this part Q to N here in this figure. Then VMN can be calculated as I into, if you see VMN and see this path, if you want to calculate VMN, it will be given by I into Ry parallel to AB. Okay, so VMN means what? This resistance AB are parallel with Ry, and if you calculate this one, the current is flowing, that is I again. So that's why I into Ry parallel to A plus B. So it will be given by I into Ry in bracket A plus B bracket complete divided by Ry plus A plus B. So same formula is again over here, used over here, but it is calculated as VMN. Now if you look at this diagram, you will understand the actual meaning of VMN, because it is clearly written over here or shown over here in a different way, but the circuitry is same. Just for understanding, it is shown like this. So this is M, this is N. Okay, and this is your R3. So this R3. Okay, now if you calculate VMO again, if you apply the voltage divider bias, then you can get VMO is equal to B divided by B plus A into VMN, because this is VMN, this is applied to this whole registry circuitry. So we are getting a VMO like this, B divided by A plus B into VMN. Now if you put the value of VMN, that is we have calculated over here in this equation, that is VMO, then you will get an equation like this. Okay, something like this. Now why we have done this? Because we have to calculate this EQMO, means this QMO, this voltage we have to calculate. So again, if you see the most important part that we have covered, that is VMO, we have calculated. Just we have to see the drop across this R3, then that will be, if you add this drop across this R3, that is IR3 plus this VMO, you will get EQMO like this. And again in this equation, if you put the value of VMO which is written over here, you will get an equation like this. Okay, so after completion of this lecture, take your time and try to solve by yourself. Okay, because it is directly written over here, you have to understand this, how it is calculated and all other things. So after completion of this lecture, take a circuit and try to derive the equation by your own, and if you get any difficulty, then you can refer this slide, okay, of this video lecture. So if you take a I common, then I will get the equation like this: EQMO is equal to I into bracket R3 plus B divided by A plus B into another bracket Ry in bracket A plus B divided by Ry plus A plus B. Okay, now for balance equation, or for balancing of this bridge, we know that EPQ is equal to EQMO. So here EPQ is equal to EQMO. This equation is equation for EPQ is written and equation for EQMO is written. Now see which part is get cancelled here. This, I think I should be gets cancelled, and it is written over here. Then this is multiplied inside, and you will get something like this. Okay, or this, we can say this, if you take B common, and we can multiply and see this, what is done over here, and please check that we are getting the answer like this. Okay, so modification is done, and it is simple mathematics. Simple mathematics is done over here. Okay, so here if you see, this part is taken over here, that is R2 divided by R1 plus R2, and after that some modification is done, and finally we get the equation like this: Rx is equal to R1 into R3 divided by R2 plus B Ry divided by A plus B plus Ry into R1 divided by R2 minus A divided by B. Okay, now see, one important thing is that this ratio AB is always equal to ratio R1, because R1 R2 are the primary, we can say, arms, and these are the secondary arms, and they are selected in such a way that R1 divided by R2 is equal to A divided by B. Okay, that is very important thing. Okay, so that you have to keep in understand throughout this calculation process. Okay, so that's why again, if you put the value here, the value of this A and B, A divided by B, then you will get the equation directly, that is Rx is equal to R1 into R3 divided by R2. Okay, so this is the beauty of Kelvin's double bridge, that we have got the equation. But one thing that is very important, that is these R1 and R2 are primary arms, and these are the secondary arms, and they are selected in such a way that R1 divided by R2 is equal to A divided by B. Okay, so after doing all the mathematics, we are getting a simple equation like this: Rx is equal to R1 into R3 divided by R2. Okay, so the primary set of Kelvin's bridge is the primary use of Kelvin's bridge is measurement of a low value resistance. Okay, and it is just modification of a Wheatstone's bridge, that you have to keep in mind. So this is the advantage of the Kelvin's double bridge. It can be used for low resistance measurement. Okay, and if you see in final equation, the resistance A, B and Ry are absent. Okay, so that's why the effect of these leads and contacts and all other things can be reached. That is again advantage of Kelvin's double bridge. Okay, so I think you got the idea behind this, and that's why if you want to measure the low resistance values, then at that time this bridge can be used. Okay, so I think we have completed two types of a DC bridge circuits, and in next lecture we will start with Hayes bridge, that is AC bridges. Okay, so before that, please see that what do you mean by AC bridge. No doubt I will discuss that, but before starting that lecture, please see what do you mean by AC bridge. Okay, and another important thing that I forgot to tell you, that what is the basic difference between DC bridge and AC bridge. That is, if you see the DC bridge, that can be used for measurement of resistance, and AC bridge can be used to measurement of impedance. And I think you know clearly about difference in between resistance and impedance. Okay, so and another important thing is that DC bridges uses DC supply, whereas AC bridges uses AC supply for its operation. That is a simple difference. Okay, so I think this is sufficient for DC bridge. Two bridges we have covered, and advantages and disadvantages also we have discussed. Okay, so this much is sufficient for DC bridge, and in next lecture we will start with the Hayes bridge. Okay, so thank you very much. Let's meet in the next lecture.